Welcome to the Data Intensive Computing and I/O Day at AdaPesc. Hope you've had a good week so far and learned lots of good stuff. We're going to change it up a little bit today and talk about not so much how to compute, but how to store your data that you get from your computations. So my name is Phil Carns, and we'll start today with sort of a I/O principles presentation. This is going to be sort of high level, but the idea is to give you some background on what these systems are like and what kind of properties they have, so that the specifics you learn later today will make a little more sense, I hope, kind of connected to why we're doing what we're doing. So we've got 4 of us speaking today. I'll introduce them in just a minute, but what we're trying to do at a high level, we work in support and research and development, and we're trying to kind of bridge the gap between what computer scientists want to do with the computing systems and the pile of hard drives that we have for you to store data on. And what this means a lot of times is characterizing what applications are doing, characterizing what the systems are doing so that we can make your usage more effective, building new software, hopefully to make your jobs easier, modeling storage systems so we can plan ahead and see what things are going to be like in the future, and basically just putting this technology into the hands of scientists. So 4 of us will be speaking today. Myself and Rob Latham are from Argonne. We've done quite a bit of software development and kind of user support over the years, things in file systems and high-level libraries and middleware. We've also got 2 guest speakers from Lawrence Berkeley Laboratory, Jailan Liu and Quincy Koziel. You'll hear from them later today, talking about, they've got a lot of experience in sort of analysis and big data and HDF5 high-level libraries. And I want you to take advantage of the opportunity to talk to us and ask us questions. In a lot of cases, some of the things we'll be talking about, you have the people who created that software in the room with you. So please take advantage of that and chat with us through the day. So what are we mostly talking about today? So HPC I/O, when we say that, we're talking about storing and retrieving data on a high-performance computing system. A lot of what we'll talk about revolves around parallel file systems. So this is like any other file system you might have on your laptop or any other system, but of course it's much bigger and supposed to be much faster. And a parallel file system and the software that goes along with it has the job of coordinating hardware components, software components, and applications to make the I/O work well. If we don't do a good job of this, you're going to waste your computing resources. You don't want to have a big allocation of thousands of compute cores and then have them just sitting because they can't get the data fast enough to compute. So most of what we'll say today is going to be about kind of nice things you can do to the file system to make this work well so you can get more compute time out of your system. So parallel file system has some differences, especially when you get to the really big ones that are on the compute resources at the DOE facilities. And I'm going to kind of walk through 5 things that I'd like you to keep in mind through the day that we'll be kind of trying to accommodate in the lectures. And we just want to give some motivation and some background for why we're going to do the things that we're doing today. So I'll start with a car analogy for the first, what's different about HPC I/O. So if you get on any of the systems, Mira, Theta, Cori, even the newer systems that are coming out, Summit and so forth, you actually have several file systems that you can use. If you compared it to cars, if you walk out and you see a bunch of different kinds of cars, you can probably get a pretty good idea just from glancing at them. What's the safest one? Which one can hold the most stuff? Which one can your buddies come with you? Which one's going to be fast? There's no doubt. I mean, you probably, without even knowing what kind of cars these are, you could tell that much. So what happens when you get onto a parallel file system or a HPC system and you need to pick your file system? These are the options that you get. Can you still tell, which of these is the right one, the one that's going to be fastest, the one that's safest, the one that's easiest to share data on? It gets a little harder. And to make things even a little more trickier is the naming isn't consistent across the facilities. So Scratch at Argonne means local disks that are attached to your compute nodes. Scratch at NERSC means a big parallel file system that's very fast. So the takeaway is just be aware that you've got multiple file systems to choose from, and have a look at your site documentation to be sure you're using the right thing for what you want to do. Some of the file systems in particular are a lot faster for sort of in-job I/O, and some of them are going to be better for saving your data later. So the websites for both sites have a table. They list all the resources you have and tell you about them, so you can kind of learn what to use. And going back to the car thing for a minute, once you sit down to use one of these things, you can probably tell then what you're doing, right? If it's in a car, maybe you've got paddle shifters. If it's a high-performance car, or maybe you've got bulletproof glass if it's a really safe car. But do you get the same kind of hints on a file system? No, they all look the same. You can open, close, read, write on all of them. There's no obvious difference between them in terms of how your application works. So is this a bad thing? Not really. I mean, it's intentional. It's for portability. So if you write an application that will run at one site, it's going to work at another site because the interfaces are the same. So that's a great thing. But it also means there's a little danger, because you can just as easily run your application on a slow file system as you can a fast file system. So just keep that in mind and use the right resources for what you're trying to do. The second thing I wanted to talk about is just kind of emphasize how big and complex these storage systems are, because this affects how you use them. I've got a diagram here from NERSC. This is one of the bigger file systems attached to the Corey and Edison systems. And it has about 10,000 hard drives. That's typical for today's HPC systems. And that means that things are going to be a little different when you try to use it. There's a lot of components that are involved in getting that many hard drives to work together to serve your purpose. So what does that mean in practice? The first thing is that although this is a very fast, a very expensive, very cutting-edge file system, some things are slow, very slow. So in particular, imagine if you wanted to move one small piece of information, say read it from a file system. That's all you want to do is get one little piece of information. To do that, you're going to be on your compute node. You're going to go through the operating system, go through the HPC network, hit a router, go to an InfiniBand network, bounce through a few switches, go to a file server, go to a disk array, go to a drive. And so there's your data. And then it goes back up all those steps that I just named. And that takes a while, no matter how fast those components are. So that means the latency is bad on these file systems. So what you don't want to do is have all of your processes waiting on one little piece of information that you have to go all the way through the network to get to. On the other hand, there's a whole lot of these paths that have these hops, like many, many paths. So what the file system is very good at is transferring a lot of data at the same time, because there's a lot of routes to get from your compute nodes to the disk drives, and they're very fast paths in terms of bandwidth. So a lot of what you'll hear today is us trying to get the really great thing about a parallel file system, which is the tremendous aggregate bandwidth that you can get if you're transferring big data in bulk in parallel, and try to get away from doing small little operations that cause your program to block while you're waiting on all these hops. So that's, in a nutshell, that's, you can go home now. That's all we need to tell you. But that's basically what we wanted to get a lot of the things you'll hear today are oriented around this. And just to illustrate with some numbers, don't worry too much about the exact numbers. These are kind of old and actually from one decommissioned system. But if you look at the graph on the left, if you have an application that accesses data using 4 kilobyte operations, maybe you'll get a few hundred megabytes per second in aggregate. That's the most you're going to get. If you're willing to access data in 4 megabyte chunks, you're getting gigabytes a second of throughput. And this discrepancy may be even bigger on a newer, faster system. And so you can get orders of magnitude improvement in how fast you can store and retrieve I/O if you just work a little bit to get bigger access sizes, bigger chunks of data moving at a time. And a related phenomenon that you'll see on the right-hand graph is how important alignment can be. What alignment means is the offset in the file that you're accessing, does it match up with where the file system divides data across disks? Because you could have one access that hits one disk or a set of disks evenly, or it could have to be split up because it didn't line up well with where the disks are arranged on the file system. And this can mean 2, 3, 4 times performance difference if your alignment is good or bad. So the takeaway from this isn't that so much that you need to carefully tune your application to accommodate these phenomenon. What we're going to try to do is give you some tools and some software that will do some of this for you so that you don't have to think about it so much. A lot of the things that we'll talk about today are kind of trying to accomplish this. The third thing that's a little different in HPC-IO, especially when you get to big, complex scientific applications, is that they have their own data models that they want to express things in. This could be a multidimensional array, it could be meshes, there could be scan lines from images that you're processing. And not only that, but almost certainly you have some attributes. You know, what are the variable names? What are the dimensions? You know, what are the most interesting data points? And that's what an application really wants to do, and you should try to stay in that domain as much as you can. But when you go to store things on a file system, you don't have all that. You have files and directories, and files are just streams of bytes. So a lot of what you'll see today is about mapping between those two worlds. How do you get from the data model that an application really wants to use down to something that the file system can understand? And you'll see this figure again later, but I'll talk about it briefly here. This is an example of how this mapping might work using a library called ParallelNetCDF. And on the left side, there's kind of a visualization of what the data might look like for an application. So there's a 3-dimensional array. It has a type. It's a double. It has a name. It's temperature. There's sizes for the dimensions. It's 1024 by 1024 by 26. There's another variable. This one's a different type. It's a float. It has a different name, different dimensions. And the software stack on a file system can help, or on a HPC system can help you map between that and a flat layout of bytes on a file system. So one thing you'll notice is that there's typically a header on a scientific data file that tells you what's in there. You know, what are the dimensions? How do you find these variables? And as an example of an optimization, that header will be set to match perfectly the alignment of the file system you're on. If you did that yourself, you might not know what the right alignment is. Should this be, is it okay if it's 100 bytes? Should it be 4 kilobytes, a megabyte? I don't know. But the tools that do this translation will line that up for you and do it in a portable way so that your file can still be opened on other systems and still kind of match the properties you want for the system you're on. The fourth thing I wanted to talk about is you'll see some of this week depending on how many different systems you're using, but these are cutting edge machines. They're built by a handful of vendors, and some of the HPC systems are as unique as snowflakes, but the file systems aren't a lot different. They're custom made for each machine that's built. They may have a little bit different hardware, a little bit different software, and as a result the performance is going to be a little bit different from site to site. And that's just something you have to be aware of. If you tune your application on one system, you get some time on another system and you run it there, there may be some different challenges in terms of your storage. So today we're going to teach you some tools that you can use to monitor your performance and see how you're doing. So if you run on one system, you go to another system, you can compare and see if you're kind of on track with your I/O, or if something's changed, there's something different that you need to accommodate there. And then the last sort of characteristic that's good to keep in mind is that storage performance, a lot more so than even compute performance or network performance, has a lot of variability on these systems. And there's a lot of reasons for this. One of them is simply that you're using so many hard drives in parallel, they're never ever all going to perform the same way at the same time. It's just not going to happen. There's too much differences between the devices, and how are they aging? Do they have problems? The other thing that's even maybe a bigger deal than that in a lot of cases is that you're sharing the storage system. You don't have your own file system that has its own, direct access that no one can interfere with. There's actually a lot of other applications, and some of them are trying to do very different things than yours is. Not only that, there's other things that aren't applications. People are transferring data in and out. There's data coming from sort of observational instruments and landing on the file system. There's data going out to have other analysis done somewhere else. There's things going to tape archive. And then increasingly, more and more, these file systems are shared across multiple computing resources. So you can look on the system and say, well, nobody's running many jobs today. I should get good performance. But there's maybe 3, 4, 5 other compute systems that could be using it at the same time. So what this means is that if you run a benchmark and you measure the I/O performance of your application, let's say you do that 5 times, you're going to get 5 different numbers. It'll be faster sometimes, it'll be slower sometimes. And this is sort of a cautionary tale for how to take measurements of your application and tune it. So I gave an example here of, this is again from a little bit older system, but the idea still holds true, is that we took 15 measurements of how long it took to perform an I/O routine at 6,000 processes on a little bit older system at NERSC, and sometimes it was as fast as 50 seconds, you finished all your I/O. Sometimes it was as slow as 63 seconds. So the thing that's tricky here is, suppose you ran your benchmark one time and you're in the sort of the 60-second range. You're trying to tune your application to get it as fast as it can so you can do a big science campaign. And you're like, all right, 60 seconds, that's pretty good. But I know this trick, the lecturers at Adipest taught me I should do this one thing that'll make it a little bit faster. And you make that change, you run again to compare and see how much better you got, and just by luck of the draw, you're down in the 50-second range. You're like, well, those guys, they told me this would be faster, it's not. So it's just something to keep in mind that you're going to get some variability from run to run. If you really want to kind of be careful about this, you want to take multiple samples if you're trying to do some performance comparison, and make sure you're getting kind of an accurate view of what's going on. And we'll have there'll be some hands-on examples through the day. We'll talk about that later, but we do have one particularly about variance if you want to try it out and kind of see what it looks like on a system that you're using now. Sure.
What is the number of samples that you usually tend to run for these type of experiments?
Well, so that's tough, right? If you're mathematically, you want a lot of them, but practically you don't have the machine hours for that. But I would say, personally, if you're just trying to do quick kind of measurements, 5 is good. I mean, by 5 you'll see like an upper and lower bound. If you were trying to publish this, you're going to want 30 or something, but I think 5 is a good rule of thumb. So just to recap the sort of concepts that I talked about so far and what you can do about it. So first and foremost, be sure and look at the documentation at your facility. You can just Google file systems, ALCF, and you'll get the chart of file systems there. And just make sure it's just a quick thing. Just point your application at the right one for what you're doing. When you're actually doing I/O in your application, do whatever you can to move data in parallel. So get the data all of your processes simultaneously. Use big operations. Try to avoid blocking on little tiny things to the degree you can. It's unavoidable sometimes, but that's just not the sweet spot for the hardware that you have here. Use I/O libraries that fit your data model. You don't have to hand code some of the optimizations we'll talk about today. We have tools that'll help you. And there's also performance debugging tools. And most of the things, well, just about everything we'll talk about today is available on any of the DOE compute facilities and a lot of the NSF ones and otherwise. And so if you learn a tool, one of the major ones that we'll talk about today, you can expect to have it available on the systems you go to and do some comparisons. And then finally, just remember that performance fluctuates. Don't just take one sample and trust that as the answer on what's going on. So one more thing though. This isn't really a system characteristic, but it's just kind of a concept to keep in mind, is that we like to encourage people to think of I/O performance as an ongoing process. It's not necessarily something you do one day or 1 week and say, okay, I'm looking at my I/O, I fixed it, it's fast, now I'm done. I'm not going to think about I/O again. The reality is things change. You may have some people modify the code in your application that may unintentionally cause it to do more or less I/O or do I/O differently. I understand this is a very difficult thing to track for a complex application. Your science objectives may change. You may take an application that you've run for years and now you're looking at a new phenomenon or a new feature, and that's going to change what you want to do with your I/O. And of course, you may simply get hours on a different machine that you've never used. So, it's a good thing to kind of periodically keep tabs on your I/O performance. We'll talk a little bit later about how to measure your I/O performance. So there's some simple things you can do in your code just to keep a kind of running look at how long your I/O is taking, and there's tools that'll help you do that. But one way to think of this, in kind of strategy and control theory, they have this thing called an OODA loop that someone invented in the military a long time ago. And the idea is that you're going to observe what's going on. And we have tools to help with this. This is using performance characterization tools or even your own instrumentation that can tell you, well, what happened? What's the raw data? How fast am I? You want to orient that. So what orient really means here is taking the background that we're teaching you today and applying that to the measurements that you get from your application to say, well, is this good? Is this bad? Could it be better? Make a decision. Is there something you'd like to try to make it faster or more efficient? And we're going to teach you what we can today, but you need to rely on your support resources too to help you. Maybe they can talk you through, I heard about this cool thing, I want to try it. And they can tell you, yeah, that sounds like a good idea, or maybe, that's not the great thing for the system you're on. And then act, implement the optimizations that we're going to talk about. So that's just, I'm not saying that, every single day worry about I/O. I know that's not realistic, but if you just keep some simple things in mind, check it periodically, see how you're doing, I think you can keep things from getting out of hand if something skews on you. So I'm going to step back from sort of this high-level principles and just show you what does an example system look like. So the one I'll talk about is Mira at ALCF. And Mira, most of you are probably familiar with it already from earlier in the week, or maybe you've used it already. That's the flagship system, the biggest system at Argonne. It has 48 racks of compute cores. There's a grand total of 786,000 cores and lots of memory. And we get big machines like this, every 5 years or so, and they tend to be orders of magnitude faster than the machine that came before. So if you stay in this field for a while, you'll see machines come and go, and you'll have to learn some new things. And in terms of what the hardware looks like, this is kind of mapping back to that picture I showed you earlier about all the things that are involved in using so many disk drives. But the biggest file system on Mira, it does have 9,000 sort of conventional, same sort of disk drives you would buy at Walmart. It's got 512 very fast solid-state drives in it. They tend to be used for metadata or small I/O. Altogether, once you formatted it and done all the safety things that the file system does, there's 12 petabytes on that particular file system that you can use to hold data. And if the stars are aligned and the wind's blowing the right direction, you can get 240 gigabytes a second off of this file system. And sort of the stack of hardware that goes together to make this happen, there's, of course, the big thing are the blue boxes. That's where your application's running. That's your compute nodes. They're not connected to all these hard drives. There's a lot of plumbing that goes to get data from the compute nodes to the hard drives. So there's a set of gateway nodes. These are the gateway nodes that bridge between the high-performance network they use for MPI and the network that's a little bit tailored more towards the storage systems. There's two networks on there. The gateway nodes are the things that cross over there. There's 300 or 400 of those. And then we have a big InfiniBand switch that connects the storage servers to the various compute systems. It's a 3,000 port switch. That doesn't literally mean there's one big box with 3,000 ports on it. It's actually a lot of little switches that are interconnected to each other to make this work. And we have a big set of file servers, and they're connected to cabinets full of hard drives that have some redundancy, ability to keep going if hard drives fail and so forth. So this is the thing that we're trying to kind of wrestle into getting the performance that you want. And in terms of the software stack, to get across these levels, you start your application's data model, what it wants to store, what it wants to retrieve. And we usually use libraries that are geared towards your model. I listed 3 example ones that are popular: HDF5, Parallel Net CDF, and Adios, but there's a lot of other ones that are maybe a little more specialized to a particular science domain. I think Rob will talk about, at least briefly, some of those later. Right below that, we have middleware. The MPI standard, which I think you guys have already heard about earlier this week. Yes, MPI? Yeah, all right. So there's a part of MPI that's MPI-IO. This is does the same sort of thing for file systems as you would get for messaging, kind of standardizes it. And the I/O middleware is where a lot of the optimizations live. So if you have many processes that are all trying to do I/O at the same time, MPI-IO kind of organizes them into a nice pattern and passes it on to the file system. We have the forwarding layer. This is the software that does the translation across networks to get to the storage system. On Mira, it's an IBM product called CIOD. And then you get to the file system, and on Mira, this is a spectrum scale file system. Some people, the old name is GPFS, and then of course the hardware. And so there's a lot of moving parts here, a lot of software, a lot of hardware, but we really want you to just focus on the things that touch your application, and we're going to teach you tips and tricks so that the things you do at that level will trickle down and make the right things happen at the lower levels. And that's pretty important because if you go to other systems, just to compare this, our other big system at Argonne is Theta, and we'll be doing experiments on Theta later today. It's a Cray system rather than an IBM system, and a lot of things are different. The parallel file system is entirely different. It's written by different people, made by a different company. The I/O forwarding, again, is totally different. The hardware architecture is different. There's different software there. It's really more of a router that's translating packets. The I/O hardware is different. It's built by different people, has different hard drives. So that's kind of concerning because things could be a lot different. But the high-level libraries, the things that your application does, actually aren't that different. You're still using HDF5, parallel netcdf, adios, or just using files and directories if that's the thing that works for you. And moving forward, we don't know what the next systems will have. You've probably heard some about things that'll be coming down the line in terms of what to expect for computing architecture in the future. There's changes that will be coming in storage systems too. There may be object-based storage, there may be non-volatile memory. Of course, new file systems are coming from different vendors. And what we're trying to do is hide that as much as we can to the application-facing stuff so that hopefully you don't have to worry too much about all that stuff. Maybe you can sometimes to get more performance, but if you sort of learn some principles and apply it at the highest level, we hope it'll trickle down to whatever technology you're using. I think I ran a little bit fast, but that's what I wanted to cover for the sort of I/O principles. Do you have any questions from anybody?
You said on the switches there was something like 3,000 ports. Does this mean that 3,000 MPI ranks will be able to communicate simultaneously, or?
Sort of. There's some funneling that goes on, so there's obviously a lot more ranks than that on the compute system. And part of the forwarder or the router's job is to kind of condense that into fewer paths. The reality is the file systems that we get can't handle 700,000 people trying to do operations at once. So it gets filtered and combined a little bit, and then it goes into the smaller network to get there.
So even still, you would suggest that using many ranks to submit pieces of data is better than...
Yeah, the more information you can give to the storage system about what it is you're trying to do, the better it can kind of aggregate that. Sometimes if you try to over-optimize by trying to line these things up, it can get a little fragile. It usually does a good job of organizing.
Just speak of the, looks like the difference between the CDF and the file, since they both have those file systems.
Well, Rob will talk to you more about this later, but I can give you sort of the simple view from my perspective is that both of them use the same data format. So netcdf is the data format so that tools can interoperate with it. Both of them, I believe, now have a parallel interface as well. The parallel netcdf that we'll talk about today is a little more tuned towards this big scale. So it's a little better at organizing thousands or tens of thousands of compute cores, but whichever one you use, you'll end up with the same file format and be able to use the same tools on it.